What's the easiest choice you can make? Window instead of middle seat? Picking a vendor who sends a great gift basket? Outsourcing business tasks you hate? What about selling with Shopify? Whether you're selling a little or a lot, Shopify helps you do your thing, however you cha-ching. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage to the first real-life store stage, all the way to the did we just hit a million orders stage. Shopify's there to help you grow. Whether you're selling scented soap or offering outdoor outfits, Shopify helps you sell. Wherever and whatever you're selling, Shopify's got you covered. Sign up for a $1 per month trial period at shopify.com/try. Go to shopify.com/try now to grow your business, no matter what stage you're in. Shopify.com/try.
Get everything for your next project today at Menards and save big money. Keep your walls and trim protected while you paint with Scotch Blue Painter's Tape. It's designed for use on multiple surfaces and can be removed easily without leaving residue behind. Save big on Scotch Blue Painter's Tape from Menards. Also, view our weekly flyer on menards.com and check out all of our great deals happening this week.
Save big money at Menards.
Real quick, before we get started, we'd like to talk to you about another podcast. It's called the Mad Scientist Podcast. And Chris Cogswell was actually on one of the Breaking Math group episodes, BFNB1, if you want to look it up. And they do episodes on a lot of weird paranormal phenomena and how they relate to science. They do episodes, for example, on the color blue, water fluoridation, magical clothing, flat earth theory, even chemtrails. So if you'd like to learn something while learning about these topics that you're going to have to learn about anyway, please check out the Mad Scientist Podcast, where podcasts are found. And now, time for your feature presentation. The fabric of the natural world is an issue of no small contention. Philosophers and truth seekers universally debate about and study the nature of reality and exist as long as there are observers in that reality. One topic that has grown from a curiosity to a branch of mathematics within the last century is the topic of cellular automata. Cellular automata are named as such for the simple reason that they involve discrete cells, which hold a usually finite and countable range of values, such as on or off, or A, B, and C. And the cells, over some field we designate as time, propagate using simple automatic rules. So what can cellular automata do? What do we learn from them? And how could they be involved in the future of the way we view the world? All this and more on this episode of Breaking Math. Episode 27, Peer Pressure. I'm Jonathan.
And I'm Gabriel.
And you can find us on Facebook at Breaking Math Podcast, Gmail at breakingmathpodcast@gmail.com, or you can go to our website at breakingmathpodcast.com, or you can visit our Twitter at Breaking Math Pod. And with us on today we have...
I'm Chris Burnett from the 10 Drink Minimum podcast.
Now, real quick, how did the podcast get started and what's it all about?
It started about 11 years ago. I was mowing lawns for a job that I had, and it's very boring, so I would listen to music on my iPod, and after a while I kind of got tired of the music I was listening to, so I went on iTunes, and I was just checking things out, and I saw something called podcasts.
Is that the era where it was Ricky Gervais show and things like that?
Yeah, Keith and the Girl. What was that was a big one. Dawn and Drew, those were big ones. And so I started listening to these shows, and I was like, well, hey, these are people doing a radio show from their home. I was like, I could do that. And so, I went to Radio Shack, and then the rest is history. Pretty much I would characterize our show as kind of a beer and lifestyle show. We talk about a lot of craft beer, and then just kind of, it's like your friends sitting around after having a couple beers, just, talking about life in general and everyday things that happen to them. So,
and that can be found anywhere podcasts are found. And that, again, is 10 Drink Minimum. And you just heard Chris Burnett.
I'd also like to mention that 10 Drink Minimum and Breaking Math are both native podcasts from Albuquerque, New Mexico, in the United States of America, of course, which is pretty cool. They've been around for quite some time, 11 years, and we just passed our first birthday, so it's pretty cool.
Happy birthday.
Yeah, thank you so much. Yeah, that was back in, a little ways, a little while ago, back in February. But I'm very impressed with the podcast scene. It's so cool. There's so many diverse interests, including a podcast about beer and culture, and then, of course, podcasts about math and
Which one's that?
Oh, the math one, crystal math. I think. I'm just kidding. Breaking math. So yeah, we're very glad to have you as a veteran podcast. We're honored to have you on our show. Thanks for showing up.
Glad to be here.
Yeah.
Now, since you're an honored guest, we're going to give you a chore.
Oh.
Could you read the Ask Math question, which was submitted by a friend of the show?
Okay. Hello, Jonathan and Gabriel. I'm a longtime listener and a big fan of the show. This is my first time sending in a question. I'm curious about a quote from Einstein. Einstein famously had said something along the lines of, "Despite persistent illusion to the contrary, the dividing line between the past, present, and future is an illusion." My question is, if time is an illusion, does this violate causality? Thank you very much, and I look forward to your answer.
Yeah, it's interesting that this person's writing style is almost exactly like Gabriel's, but I digress. I think that there's two ways to answer the question, the not so fun way and the fun way. Okay. The not so fun way says that Einstein was literally just talking about relativity and the non-simultaneity of events. Essentially, that's the fact that if you're going very quickly, and let's say you're going very quickly, you get a lot shorter as you go quickly. So if your car is 10 feet long and you're going very close to the speed of light, it might be 1 foot long. So let's say you see this 1 foot long car driving along at almost the speed of light, and it enters a garage that's 2 feet long. And this garage has 2 garage doors. When it's in the middle of the garage doors close, trapping the car in the garage and then open again. And then the car goes on its way. Now the question is, what would that look like for the people in the car? Because the car is 10 feet long. It doesn't fit in a 2 foot long garage. So the solution is that it would look like the garage door in front was closing, then opening, then it would go through, and the garage door behind it was closing and opening. So events that used to be simultaneous in a different frame of reference are not simultaneous.
Fascinating. That's fascinating. So basically, as you just said, we're talking about relativity. Now, I think that this writer, who, my goodness, you're right, we do have a very similar writing style. I think what also inspired this is when you talk about time and you talk about perspective. From our perspective, we can talk about our past events and every choice that we made, and things like, if you chose to go down one hallway and not the other, that has already been done. So, if you were to line up all of the events of your entire life and look at all of them, you would see a clear path. And, this is from a perspective of, let's just say, outside of time and looking at what has already happened. The thing is, though, when you are from a given point in a time frame, in a time duration, if you look at the future that hasn't happened yet, you haven't made certain choices yet. So you haven't chosen if you're gonna, go one direction or the other. So from that perspective, you can't talk about stepping outside of time because it simply doesn't exist.
Now, what you're saying is true if you assume one universal frame of reference for time, but as we've seen time and time again, time is not that was not on purpose. It's not a universal thing. Every frame of reference has its own time, so we can see that time is illusory in that sense. But we could go even a little bit further. If we see the history of the universe starting from the Big Bang at one end of a string, and the string curls around, does a bunch of loops and stuff, and at the end we have the end of the universe. We can imagine a slightly more complicated string and a slightly less complicated string. And if you listen to our last episode, you'll know that things go from less complicated to more complicated. Disorder increases. So we can imagine this string that represents all of time warping in a new time dimension. So I guess the answer is it doesn't violate causality. It appends to it. And I think that answers their question.
Yeah, hopefully. Perhaps we'll hear from this... We'll hear back from this listener again, and we'll see if that answer is satisfactory. What do you think, Chris?
I think you did it well. I don't know what you said. I'm like, wow.
Well, let's break it down then. Do you have any questions about what I said?
Probably about 1,000. But
okay. Or again, not to spend a whole lot of time, but just in terms of the original question, do you how do you feel about the original question and
how do you feel about the quote that the Einstein quote?
Wow. I don't even know how to answer that. Despite the time is an illusion. have not very good at mathematics. I failed algebra. So, when talking about, philosophical things like time is an illusion, for me, that's a very abstract construct that I'm just like, okay, well, okay, I believe you. I don't know how to break it down.
Yeah, in what sense is it illusory? I mean, illusions is usually a deviation from the senses, right. And it's very philosophical, so I see your point.
Well, yeah, I mean, from a mathematical perspective, time exists. Is time, the clock on the wall? Is it, we get older, we get, passage of time, as in, we see it on our body, we see it on the earth, I don't know.
And actually, we have our first real, not that the other one wasn't real, Ask Math question. And Gabriel couldn't be here to record this because he has a mouthful of food right now. And it goes, hello, I understand that in a multiverse, different universes would obey different laws of physics. Question, would all universes in a multiverse obey the same laws of mathematics? And that was sent in by Pablo C. Now, real quick, the laws of physics would be different. That is true. Although, as far as we can tell, they would follow certain systems of laws. For example, the fine structure constant relates different physical constants and how they interact. If we change the fine structure constant, those would interact in a very specific way. But it's possible to imagine even more exotic universes, and that is true. However, it's almost impossible to imagine different types of mathematics, because everything that we could imagine is imagined in a brain that was generated by this universe. So it's very hard to even fathom the question in a meaningful way. I use logic just like everyone else. So I think it is almost imperative to say that this question does not have an answer in our universe. Good question, though. And if you want to ask us a question on Ask Math, you could send it to anywhere, Facebook, Gmail, or our Twitter.
Yeah.
We're going to start with the definition of cellular automata.
Next, we're going to talk about grid-based cellular automata.
And we're going to finish off with a section on John von Neumann's work on cellular automata. So a cellular automata has to have a few different components, and one of those is a topology. Now, the word topology to some people reminds them of the fact that a donut and a coffee cup are topologically identical. Have you heard of that, Chris?
Yeah, they're both round when you look from the top.
Well, not necessarily like that. It's because if you made a donut out of clay, you could deform the clay into the shape of a mug without poking holes in it.
Okay.
And that's why they're topologically identical.
Oh, I see.
But what we're talking about is a very different type of topology, and it's graph-based topology. And a graph is a set of nodes connected by arrows or lines. So a grid is an example of a topology.
Okay.
Because if you, at the intersection of every cross, if you put a point there, then you have points connected by lines, right?
Right.
Another topology might be hexagons. Another topology might just be a random, bunch of stuff. You can have fractal topologies, but it just has to have a definition.
Okay.
And usually the topology is infinite or unbounded but finite, meaning that it doesn't have edges that some things just disappear off of. It goes forever. Next, there's a set of possible values. So each dot on this topology, on this graph, has a possible value. Maybe those values are A, B, and C. Maybe they're on and off, but it has to have a set of possible values. So am I making it clear that there's a different value at every intersection on a grid or something like that?
Like telling it what to do.
Well, not necessarily what to do, what to be.
Okay.
Because what to do is the next part.
Gotcha.
Because you need two sets of rules. Given any node, you have to figure out which nodes are important to that node. So in a grid, it might be the 8 neighbors of the point, the top, bottom, left, right, and the 4 diagonals. And other topologies might have different rules. But then you have to have a rule for generating new values from those nodes' values. So if I tell you that the neighbors are A, B, C, B, B, and A, we have to have a rule that says, oh yeah, next time it's going to be B. Does that make sense?
Yeah.
Okay, yeah. So essentially, the components of cellular automata include, the first thing is a topology, which is just, if you're talking about the shapes of the cells. The second thing is a set of possible values for each of the cells. And lastly, you need a set of rules for describing how the cells interact with their neighbors. And in this case, it's just their immediate neighbors. I don't think they're concerned with cells that are further away, not adjacent.
Now, what you've described is most cellular automata does follow those rules that you just laid out.
Okay.
Where it's the nearest neighbors, the neighbors literally touching the thing, and the topology is based on the shape of the cells.
Mm-hmm.
But the topology doesn't have to be based on the shape of the cells unless they tessellate.
Mm-hmm.
It or fit together on a plane.
What was that word? Tessellate?
Yeah, tessellate. Like like you ever played like with like those little like squares and triangles as a kid, and you put them into weird patterns.
Yeah.
That's tessellation.
Okay.
And so that's how most of them work. But you could have a topology that's, for example, non-Euclidean, hyperbolic, where it doesn't fit onto a grid. It maybe fits onto a sphere.
Would it still have to, by the way, just for our listeners' sake, I am very much new to this area, so I hope that my clarifying questions are helpful for those who are not as familiar with cellular automata. So in the case of a hyperbolic cellular automata, would they still have to be touching just in a different way, like not on a flat plane, but on a
hyperbolic surface, they could still be touching. There are ways to tessellate things in hyperbolic space with 7 sides. We're not going to go into that because it's complicated.
Yeah.
But Escher used that in his paintings.
Wow.
Okay.
You ever seen the painting where it's like it's like a circle and it gets smaller and smaller towards the edges?
Okay.
That's a hyperbolic space.
Is what I'm hearing correct in the sense that basically the idea that I'm trying to get around is that for the math to work or for the functions to work in a cellular automata program, they don't necessarily have to touch. They just have to have the right rules that describe the behavior.
Describe the relationships between the cells.
Okay.
So it could be like, for example, a tree structure. That could be the topology for cellular automata.
Okay. Now, in the example of, let's just say, chess, if you were to describe how a pawn takes out an opponent, that does require them to be tangential, but also at the diagonal, which I guess.
Yeah, and in that case, if you just imagine the grid, just put diagonals in the grid. Okay. So across every box, draw an X in every box. Got it. That's the topology for what's called the game of life that we'll go over in 2 sections from now.
Okay. I think I'm following.
And weirdly importantly, but it seems obvious, and that's why I left till the end, is that you have to have a starting position or arrangement. So that's where you assign a different value to every node in the topology.
Okay. This reminds me a lot of our evolutionary algorithm that we programmed last year or other similar programs. And it makes me wonder what would happen if every single value was identical at the beginning of a cellular automata.
Actually, that's pretty interesting because if you look at, go to our episode TMI about information theory, you'll see that a set of ones and a set of zeros are just equally uninteresting. Mm-hmm. It kind of works the same way in cellular automata. There's actually a lot to do with chaos and randomness. But really, the starting positions for interesting cellular automata have to be themselves interesting.
Okay. So in other words, you wouldn't want all the same starting position. You would want a little bit of chaos. That's why in some example, like if we wrote a program here where, we had Chris, I guess, draw his name, Chris, where it basically, where it marked those squares were darkened, that added some change, some entropy to it.
Yeah. And I wouldn't say that you need to start out with chaos. You need to start off with structure.
Right. Okay.
But yeah, that's what you need for cellular automata. But one thing that I really want to stress about cellular automata is that they're 100% predictable. There's no such thing. There are cellular automata that have random rules, but those are a different thing entirely. They're usually a strict set of rules. They're like chess, not like poker.
So what you're saying is what looks like chaos actually isn't chaos. There's actually there's actually where it's actually going to go if you really broke down and got into it and did the actual
What's weird is that chaos and what I said actually do work simultaneously, because chaos has to do more with sensitivity to initial conditions. So, for example, like there's, as we'll see in a bit, some very smart cellular automata. And if you imagine these like a person reading a sentence, if I read the sentence, the blue sheep went to the store, it's a different sentence than the sheep went to the store. So the understanding will be different, and the whole thought process or chaotic process, whatever you want to call it, will be different.
I like your analogy of a sheep going to the store. How'd you come up with that?
Right.
Because I went to the store the other day and I tried to imagine something that could be blue, and for some reason my mind came up with sheep.
Okay.
Oh, I thought you were going to say you went to the store and there was a blue sheep there, and I was like, wow.
Okay.
What story?
Yeah.
The sheep store.
The sheep. For this next part of the podcast, we're going to talk about a researcher who is quite famous called Dr. Stephen Wolfram. He's a very interesting guy. He actually wrote a paper when he was 18 on quarks, which has been very, very highly cited. And for those who may or may not be aware, quarks are the subatomic particles that make up protons and neutrons. So
that's what I was wondering. I was like, what are quarks?
Yeah, very, very interesting stuff. We should do an episode on quarks, because then we can talk about, well, what are quarks? We can then talk about what are quarks made out of, and that gets very interesting. So Dr. Stephen Wolfram wrote about quarks when he was very young. He also developed the program Mathematica.
There's also an online version of Mathematica, or like Mathematica Lite, called Wolfram Alpha, which you may have used. And it's really cool. Gabriel, if you type in the sentence ratio between population of Albuquerque and population of Denver into Wolfram Alpha, do that real quick.
Cool, I've done that. So it says that the result is, for the ratio between the population of Albuquerque and the population of Denver, is 0.807.
And if you look at the next thing, it's a graph of the ratio. So it'll tell it, like, it does the stuff on the fly. It's really
My goodness,
cool.
Yeah, it shows from even before 1995 up until the end of the graph is actually about 2016, looks like.
Yeah, but it doesn't show how much better our green chili is than theirs. It doesn't show that at all.
They
That's
don't
right.
have green chili.
You know what?
Right.
For all of our listeners, green chili from New Mexico is superb. It's a little spicy, but you put green chili on your hamburgers or on your scrambled eggs.
They think they do.
Yeah, it's phenomenal. And recently, Colorado's been growing some green chili, but
Yeah.
They've been doing it wrong because they're not us.
yeah, exactly.
But essentially, yeah, so he's a researcher, and one of the things that he researched a lot of was cellular automata. And he did a lot of research, and he wrote a book. This episode is all about cellular automata, which is a field of discrete math. To get you ready for this kind of math, our partner Brilliant.org has a course on number theory, which will help you learn things like modular arithmetic and factorization, which have close analogs in cellular automata. Actively working through these problems is sure to get you up to speed. To support your educational journey in math, go to Brilliant.org/breakingmath and sign up for free. The first 200 Breaking Math listeners get 20% off the annual subscription, which we've been using. And now, back to the episode.
That's right. The book was called A New Kind of Science. And in that book, basically, he talked a lot about cellular automata and his work, right?
Yeah, and one of the things from the book is that he separates all cellular automata into 4 different classes based on their long-term behavior. And in A New Kind of Science, he talks about different classes of cellular automata, and he breaks them into 4 different classes.
Right. The first class of cellular automata that he talks about is a type that settles down into a homogeneous state, which is much like a pond where you throw in some stones and eventually it turns into a flat surface.
These are the least interesting cellular automata. They basically don't have any interesting behavior, and they don't have any long-term behavior.
But it is a cellular automata in the sense that the ripple spreads in all of the cells or all the water molecules at the surface.
You could model that as a cellular automata where maybe like the height is the value that the cells have.
Okay,
the
cool.
height of the water.
Interesting. Gresh, do you want to read our next class?
Some randomness stays, and the structures that developed are either stable or oscillate. This is like throwing a bomb into a guard tower where the guards are given orders to stay calm and be routine.
Were you inspired by playing Call of Duty?
Right.
I was actually inspired by
Wolfenstein.
what's that movie about the orcs and all that in the
Lord of the Rings?
Lord of the Rings, where they have a battle at one point. and they light stuff, and everybody does chaotic stuff, but then they form a new structure entirely. And that's what happens with these. There's some oscillators, which means that maybe some guards are walking around a perimeter. There's some stable structures, which might be like a phalanx. So that's what the cellular automata are.
And then obviously, and again, I realize this is a bit of a cryptic example here, but in the example where there's a bomb, and probably anybody who was in the proximity of the bomb would be running away from it. Like, in other words, breaking order.
Oh yeah, the bomb represents more in this case, in this analogy, a source of information, a source of randomness or entropy.
Okay, nice, interesting.
So then there's a third one where most patterns behave chaotically, and the whole structure tends to be more or less sensitive to initial conditions equally. So these are really chaotic ones, and nearly all patterns evolve in a pseudo-random manner. And I say pseudo-random because there is some predictability to some of these patterns, but more often than not, they're unpredictable.
So this brings me back to our second episode ever of Breaking Math, Wreaking Chaos. So when we talk about just a chaotic system, you mean something like weather?
Oh yeah, something like weather, where the flap of a butterfly's wings will change the order of tornadoes in the world. They won't change how many tornadoes there are, but it'll change when they happen.
Okay. Now, and again, what I'm trying to do is be clear about what differentiates this third class from the previous class.
This one is different because it's literally like in the last class, the guards, after a while, they settle into a new routine, right?
Got it. Okay.
But in this one, local changes to the pattern tend to spread indefinitely.
Okay.
So it's like running through a group of pigeons. The pigeons affect other pigeons, and then it just spreads chaotically.
Okay. And again, I fully realize this is a dark example, but this would be like if there were maybe multiple grenades hurled into the guard tower over time. Gosh, I need a less dark example here.
Well, I think the guard example is better for number 2 because the guards have their orders and they know how to reorder themselves. In this one, it's that I chose pigeons because because they're dumb animals.
No offense, pigeons. For our last class, I'd also like to hand that off to our guest.
Number 4,
Yes.
less random than number 3 and conjectured to be capable of universal computation. These patterns from the most interesting, if lengthy, long-term behavior. This is like the universe.
Wow, sorry. This is like the all-encompassing class. This is I could easily have read that and thought, what did I just read?
Yeah, that's kind of what I'm at.
Now, basically what universal computation is, it's the principle that
Save big this summer with great deals, all in the Baker's app. Get red, green, or black juicy seedless grapes for $1.88 per pound with a digital coupon. Then buy 2, get 2 free delicious 12-packs of Coca-Cola, Pepsi, or 7-Up, all with your card. Shop these deals at your local Baker's, less than 10 miles away. Or tap the screen now to download the Baker's app to save big today. Baker's, fresh for everyone. Prices and product availability subject to change. Restrictions apply. See site for details.
Get everything for your next project today at Menards and save big money. Keep your walls and trim protected while you paint with Scotch Blue Painter's Tape. It's designed for use on multiple surfaces and can be removed easily without leaving residue behind. Save big on Scotch Blue Painter's Tape from Menards. Also, view our weekly flyer on menards.com and check out all of our great deals happening this week.
Save big money at Menards.
no computer can do something that another computer cannot do. Every computer can simulate every other computer if it has enough memory.
Correct.
And in these patterns, if you put the right cells on or off or change them to A, B in the right order, like you could basically build a computer within the simulation. And you could actually simulate the simulation within the simulation. And
okay, so this is actually applicable to some of the recent, if perhaps outlandish things said by Elon Musk, where he talks about our universe actually being a simulation.
Right.
Or maybe another example would be the phenomenal episode of Rick and Morty in which he makes a car battery that's actually a small universe, and in that universe they produce energy.
A little bit, but in that case, he had an accelerated unbounded vacuum. In this case, it would get slower technically each time.
Oh, of course. How did I overlook that? Sorry.
So what you're saying is, like, if you have a computer, then you could virtually inside that computer build another computer.
Yeah, and you could build the same computer, but it would be a little slower, right?
Right, of course.
Because you're simulating the wires that the computer already has with fake wires.
Right.
And you can imagine simulating that computer on itself, like a third layer, right?
Right.
And
Wow.
you could do that infinitely.
And it would lose
Russian
power.
dolls.
It would get slower every time.
Yeah, and the thing is about these though is that they're not that common. These patterns, most are 1, 2, and 3. Number 4 we still don't know what characterizes these. We don't even know if they're all capable of universal computation, but Stephen Wolfram thinks so, and I happen to think so. So those are the 4 classes of cellular automata.
Man, I actually sincerely would like to go into Photoshop and make examples of all 4 of those. Maybe I will. And again, so since I see these grids and this kind of behavior, I think of even things like rashes on your skin. Could that be considered cellular automata?
In that case, I'll just build a quick cellular automata that you might be able to simulate. Imagine you just put a bunch of dots on your skin, connect them with lines. If more than half of or if more than a third of the dots connected to a line are infected, then that dot becomes infected.
Oh, wow.
But if it's infected for more than 3 generations, it starts to heal. I didn't make that rigorous. That's an exercise left to the reader, but that's an example of a cellular automata that simulates that kind of system.
I love to leave exercises to the reader. They're such a reminds me of my old math
You
textbooks.
do the math.
If you have a game of life pattern that simulates a computer,
Mm-hmm.
let's say you just kind of like throw a wrench in the pattern, like you turn a cell off that was on or A that was B in the wrong place, that has a potential to destroy the entire computation slowly, like from the inside out. So that would be more of a flaw in a flaw in a pattern in the cellular automata. But there's
wow.
really cool things you could do with them, as we'll see in the next section.
Crazy.
All right, now we're going to talk about grid-based cellular automata. We went over what it would look like in 2 dimensions, but we're going to go even simpler. We're going to do 1-dimensional cellular automata, where time is more of a spatial dimension. So an example of a cellular automata that you can generate is the Sierpinski triangle. Chris, are you familiar?
I've never heard of it.
The Sierpinski triangle, you ever draw a triangle and then you draw an upside down triangle that divides it into 4 different triangles?
Yes.
And then you keep going that with the
Yeah.
ones
Like the
edges?
Triforce, right?
Yeah, like this generates a Sierpinski triangle. Rule 22 is what it's called, and it's called 22 because if you look at the neighbors of a cell and the cell itself, there's 3 different cells there, right?
Mm-hmm. Yes.
And the cell can either be on or off in these binary grid-based cellular automata that we're talking about.
Yes.
Okay.
So what you have to do is, if you imagine time as being like the vertical axis, you could just say that every time there's a new generation, you just add a new row.
Okay.
So what you do for every square is you look at the one above it, the one up and to the right, and the one up and to the left.
Okay.
And if all 3 are 1, which is the binary number 7, then it's off.
Mm-hmm.
If it's 1 1 0, it's 0. If it's etc. And the pattern is 0 0 0 1 0 1 1 0. Now that sounded like gibberish, obviously, so I'm going to break that down. In this case, what it means is that if the one up and to the left is on and the other 2 are off, then the cell is on. If the cell is on itself and the other 2 are off, then the one below it just turns on the same way. And if only the one to the right is on, then it turns on, but otherwise it's off.
Interesting. So what I was trying to follow along, and I kind of lost you just a little bit. I was trying to think about the rule, like the and or like are these and or ors?
In this case, it would be a variant on an exclusive OR gate, I think.
Okay.
Yeah.
Because what I was thinking of, based on if it's triangular, based on the location, it would have 2. I guess you'd call them parents. Am I thinking about
Well, it's not
this?
triangular, it's a grid.
Okay.
But each one is based on the one above it, the one up and to the left, and the one up and to the right.
Okay. Got it. I'm
If you
following.
draw a dot,
Yeah.
then because then the next row will be 3 dots.
Okay.
And then it'll grow into a Sierpinski triangle.
Okay, I got it. Cool. So then, yeah, and as you said earlier, this basically can be summarized as what you said earlier, the 0 0 0 1 0 1 1 0, which in binary is
22.
22.
yay. Awesome. Okay, yeah, that makes sense.
The rule 22 would be an example of a rule of a class 2 automata, because if you have kind of a random starting position, you'll have like things that look like Sierpinski triangle stuff, but it's going to look a little random. So the randomness kind of stays, the amount of information stays, it doesn't dissipate, it doesn't turn to nothing.
Okay.
And that's in contrast to a Rule 3 cellular automata. Remember, Rule 3 is chaotic, almost pure chaotic behavior. And if you're near a computer, just search the term Rule 30.
Okay, interesting. Of course, as we said earlier from the precedent, Rule 30 probably has a representation in binary. And I'm sorry, did you say that Rule 30 corresponds with Class 3?
Class 3.
Okay. Interesting.
Now, Chris, you have a picture of Rule 30 in front of you.
Yes.
What can you describe it to the listeners?
It is a triangle on that's kind of bisected down the middle. On one side, it looks like there's a pattern going one direction, and then on the other side, the pattern is very chaotic. That's the way I see it. I don't know.
It's very chaotic.
So to me, this almost looks like, as Chris exactly said. So the left side to me looks like tire tracks where everything is in one direction. Like one tire drove over the whole thing, and you've got all these. Yeah, and on the right side, it's just gravel. But when you look up, when you zoom in, it's a bunch of triangles
of varying sizes.
Yes.
And at random places too.
Right. Yeah.
Yes.
And what's interesting about this pattern is that for a while it was conjectured that it could be used as a random number generator.
Okay.
After a while, it turned out that was wrong. But
Oh, interesting. Okay.
yeah, there are patterns that could be found. Very wrong.
Okay, so here's my question then. Is it more random than pseudo-random? Because I know that pseudo-random that our computers use isn't really random either.
Oh yeah, no. This is completely deterministic, so it's just as random as pseudo-random.
Okay, interesting.
And this pattern is actually found in nature in the Conus textile mollusk shell. The Conus textile mollusk grows in a spiral shape, so it has generations that go down. And you have a picture of the mollusk in front of you.
Yeah. That is pretty cool. It is pretty much that,
Yeah, you see the same triangles and everything.
So with this mollusk shell, clearly, as we've all seen with shells, especially seashells, they are based on a certain repeating spiral. I've seen in the past, I think a lot of folks are familiar with the Fibonacci spirals, which this may or may not be. I don't know.
No, it's not really Fibonacci. It's a very random pattern.
Okay.
It just happened to show up one place in nature.
Okay. Oh, and now in that case, I was talking more about the physical shape of the shell, not the pattern on the shell.
Oh, I see. Yeah, the pattern on the physical shape of the shell is very predictable, but the pattern on top of it is very chaotic.
Okay. Yeah. That's interesting. So yeah, it's like if you were to turn this into pixels, then you have either a Rule 20 or a Rule 30 or some other rule, and you get this crazy pattern, which is it is cool. It's pretty.
Yeah, that's very interesting. How there is some. It looks like there's a pattern, but it's not like you'll have like the larger triangles, but then there's like a line of triangles that kind of go up at an angle, and then there's just places where there aren't any at all. That's very interesting.
Oh yeah, for sure. And I want you to do something real quick. Do you have a sheet of paper or 2 credit cards with you?
No.
The credit card here. I will loan you my credit cards here. Is this a wise move? Is this a wise move?
Let me just log into Amazon real quick.
Now put one credit card on go to the Class 30 rule, and put it on the random side of the screen.
Okay. So, and what's funny is I'm completely cognizant of the fact that we're doing a very visual visual concept.
So just stick it
on an auditory podcast.
Yeah, just put it on the screen, and then put the next credit card next to it so that there's about 1 pixel of separation. You'll notice that there's no discernible pattern in a strip of this pattern.
Oh, okay. So with the I see what you're doing. 2 credit cards, put them together so you only see one single strip. And we're looking for a pattern in there. What do you see?
I don't know.
You can read your fortune if you interpret.
The pattern. I mean, I don't really see a pattern in it.
Yeah, there's no pattern. Yeah. So even though the triangles look like they're kind of forming a pattern, really, if you look at the way this is distributed, it's still totally random.
I see.
Yeah, kind of the same thing with like reading tea leaves, right?
A little bit, yeah.
Hey, that's real, man.
Reading. We should do that. Wouldn't it be horrible if somebody decided to make a fortune teller app that was just Cellular Automata?
I bet there are some.
I'm sure there are. Okay. And then say vague things like, you will experience a surprise today. When will it come? It's a surprise.
And then, so we have now 2-dimensional cellular automata, and one of the most famous ones is the game of life.
This is so fascinating. I love the term "the game of life" because I've seen this before, and it is a cellular automaton. I think that the idea here is that this can arguably simulate all of life, right?
Yeah, it is a class 4 pattern. It's capable of universal computation. So anything that could be computed on a computer, like the universe, arguably, can be simulated in the game of life.
That might be troubling, depending on how you look at it. Just this whole argument that all of life and all of its complexities and relationships and changes can be broken down. So is this? I mean, I guess my question is it arguable that this, is it tongue-in-cheek game of life, or are people saying that this...
Well, the reason why it's called the game of life is because it was originally designed as, instead of the cells being on and off, we're going to call them living and dead.
Okay, I see.
That's why it's called the game
of
life.
So this isn't some existential spiral.
No.
Okay.
When Conway came up with it, he didn't know that it was capable of universal computation. He just thought it was cool.
Okay. So in this case, strictly speaking, to clarify my previous question, this is called the game of life because these cells are not zeros and ones, but rather they're called living and dead.
Yeah, that's essentially it. It's just he could have called it like super moss. He didn't really
awake and asleep or something.
Yep.
Yeah.
Okay.
But we're going to use alive and dead. So just imagine an infinite grid, and every cell has 8 neighbors, right?
So if it's 8 neighbors, then is an individual cell then is not going to be a square. It's going to be a...
No, it's a square, but it could go diagonal too.
Got it. Okay, so the diagonals do count then. So yes, 8 neighbors. Okay.
And so if a cell has less than 2 living neighbors, it dies because it goes extinct. It's underpopulated. Okay,
so it's lonely and it's depressed and it dies. If it has 2... 2 or under, or is it
under 2?
So if it's got 1 or less, I understand. Yes.
If it has more than 3, so 4 or more living cells, then it dies in the next generation because of overcrowding or because it was already dead.
Oh, okay. Got it. Okay.
If it has exactly 3 neighbors, though, no matter if it's alive or dead, it becomes alive in the next generation or stays alive.
Sorry, if it has so in this game of life, dead things can come back to life.
Yeah, and that's kind of like breeding, like almost.
Okay, I got it. So, and you're saying is if a cell has exactly 3 neighbors that are alive?
Yeah.
Understood.
And if it has exactly 2 neighbors that are alive, there's no change in the state. If alive cells stay alive and dead cells stay dead, but there's not anything we really care about.
Wow, that does sound pretty crazy. So obviously we can't do an infinite grid. We can only do a finite grid. But this still has me very curious as to what it would look like if we...
Well, we can simulate an infinite grid because we only have to keep track of the cells that are on and their coordinates. And as long as we don't have an infinitely large pattern that has infinite information, we could simulate it on an infinite grid.
Okay. Very good. Will we have that opportunity?
Well, yeah, totally. We're going to do that in just a second. But first, I think we should tell the listeners how to play the game of life on a checkers board, like some of the original people did this.
Oh, okay. Very good. Very good. So if you don't have a fancy schmancy computer that all the kids have these days, so you start with 2 different markers, let's say beans and pennies. And then let's say we have a pattern on the board with just pennies, where pennies represent live cells.
So this is your starting or current position.
Okay. Yep. And then what you do is you put 2 beans on the cells which will be alive in the next generation, and 1 bean on the cell that will be dead in the next generation.
So now you know which cells you visited and which ones you haven't, because the ones that you haven't that you have visited all have beans.
Okay. Yeah. Then all you do is you go through and you take off all the pennies, and then you take off 1 bean of each cell, and you repeat this.
Yeah, and then that's how you can play it at home.
Yep. Are you going to go home and do this,
No.
Chris?
No, it takes an absurd amount of patience to do this by hand. It took me like a week to figure out how to find. I had like a bunch of graph paper that was just scribbles because I was trying to figure out life patterns without a computer.
So this is the kind of thing that Jonathan does in his free time. In case you're wondering, he tries to do Cellular Automata on his own. Awesome. We're very glad that people like you do this. We will live vicariously through you.
I'll take your word for it.
Yeah.
Don't take my word for it. Try it at home. But
or if you're babysitting and you want to occupy your kids for a while.
And it was invented by John Conway, who's a mathematician. He, as I recall, he's done some work in group theory that might not be correct. But this is a major contribution of his that he seems to be a little bit annoyed that it got so big. in interviews. He seems a little annoyed to me.
Wow.
He's annoyed that Cellular Automata got so.
No, the game of life, because he didn't invent Cellular Automata. He just invented the game of life.
Okay.
Wow.
It kind of took on a life of its own.
Yep.
Because you model the popularity of the game of life using Cellular Automata.
So just to show you the kind of cool things that exist in the game of life, there's a whole vocabulary that has sprung up and communities that have sprung up about the game of life. And there are things called still lifes. And these have the property that in the next generation, they stay exactly the same as they were before. They have fun names like the loaf or the tub or the boat. And these are very simple patterns. They're just a few live cells, but they have the property that they stay that way. They do, yeah.
A loaf, like a loaf of bread.
Yeah, it kind of looks like a loaf of bread.
Interesting. So I'm looking at pictures here of these still lives. These are just like what is this grid, like a 6x6 grid, and you just have a few of them shaded in. So you've got like looks like almost a crooked smiley face or something.
It's
or even an old Atari Asteroids.
yeah, asteroids ship or something.
Okay.
Then there's what are called Gardens of Eden, and they have the property that they're impossible to generate from a previous pattern. They're called that because only God, which is the person making the patterns, could have designed them.
Oh.
That's kind of cool. That sounds powerful.
So this tells us real quick about this simulation that it might be infinitely potentially complex, but it's not all-encompassing. You can't generate every single pattern using the game of life. Some patterns are impossible to generate from others.
Interesting. And then there's also a pattern here I'm reading called oscillators, and I think that breaks down into two subcategories. There's a category here called oscillators. For example, there are blinkers.
Which have a period of 2, which means that they go from one state to the next one and then back again. Okay. So it goes dun, 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 dun.
Like blink. They blink.
They just blink.
Yeah, they blink.
And then there's another kind of oscillator here called a pentadecathlon. I'm sorry, what?
Pentadecathlon.
Pentadecathlon, which is not a dinosaur. It's it has a period of 15.
Yeah, which means that it takes 15 generations to get back to its original form. And that could be said of any of the forms within it.
Interesting, but so as an oscillator though, it always returns back to its original form.
Yeah, exactly back to its original form.
Unlike Pokemon, but perhaps like the Incredible Hulk, maybe. I don't know.
I'm not familiar enough with the Hulk.
He can go back to human after a while.
Oh, like that. Okay.
Came into the Hulk back.
Yeah, I get it now.
Okay, and then there's other examples here. One of them here is called looks like spaceships.
And these are oscillators where when it gets back to its original state, it's displaced. So it might be like one cell up and to the right or one cell down to the left.
Okay.
They basically move. The pattern moves over time.
We've got a few examples of spaceships. You want to read those, Chris?
A glider and a LWSS or lightweight spaceship.
And these are small patterns. They actually kind of form spontaneously.
But man, this is cool. I kind of want to be part of the culture of the game of life. That would be fun. Minecraft. I wonder how much game of life you could do with Minecraft. Is that possible?
Yeah. I hate that I know this, but you just need a lot of redstone.
Okay.
So
very good.
Now we're gonna open up the game of life and do a quick simulation. Open up your game of life and delete everything.
Sure, absolutely. Okay, so I have a game of life right here. I'm going to walk my audience through it. So I've opened it, and what's the delete all?
Just Control A.
Oh yeah. And then delete. Okay, so I've got this game of life simulation pulled open.
So the pattern that we're going to be exploring is called the R pentomino, and it encapsulates a lot about the game of life itself.
Okay, so here we go, and I've got the pencil. So two across, 2 down. Okay.
Now what's cool about this pattern is that it's a very simple starting pattern, but it has very chaotic behavior that stabilizes after a while. It starts with 5 cells, hence the name pentomino, and it ends with 1,103 different cells. So why don't you press play on the simulation?
Okay. You ever tried to teach your aunt or grandma how to use the Facebook? It's like, okay, where's play here? Whoa.
Wow, it's like almost looks like explosions all over the place.
Yeah.
And then there's the little gliders that are flying off the bottom and one off the top.
Yeah, so you see these stuff forms spontaneously.
I think all of our listeners, let me tell you with full enthusiasm, get yourself a game of Cellular Automata and bring it to your next Tinder date. It's epic.
Yeah.
Okay, so
And I misspoke earlier. It has 1,103 generations until it stabilizes with a final population of 116, not 1,103.
So yeah, it's kind of stopped. It's not doing a whole lot now.
Yeah, so it's stabilized.
Yep, exactly.
Now, if you'd like to see the Game of Life, you can either go to breakingmathpodcast.com/gameoflife.html, or you could go download a program called Golly, and that'll allow you to do your own patterns.
And yes, that's golly, as in what you would hear your grandma say when she drops her tea.
Golly.
Yeah, and Golly uses an algorithm called HashLife, which can simulate very large things. You could simulate literally, I think one time I simulated 1 to the 120 generations of this one pattern. It's a very efficient algorithm. But as soon as you throw a wrench into it, as soon as it gets more interesting, it slows down.
Wow.
So it's a very conservative algorithm, but it's a lot about that. And we don't have time to go into it because it's a very complicated algorithm. But if you are algorithmically inclined, check out HashLife.
As most are.
Nice. Awesome.
Now, the last thing we're going to talk about is a really cool cellular automata. It's one of the first ones ever made. It was made in the 40s by John von Neumann. And instead of having 2 states on and off, it had 29 different states, depending on the function of the cell. And each one had like complex rules. It's a very complicated thing. But it's capable of universal replication. And he did this without a computer. He used graph paper to design this incredibly complex system.
I bet his wife loved that.
What's that?
I bet his wife loved that.
I'm not sure if he ever married.
Oh, okay.
Yeah.
Now, the way that the universal replicator works, and any universal replicator, including ones that do exist within the Game of Life and actually are preloaded into Golly, work on the principle of quines. And we've talked about quines before. An example of a quine is yields the sentence when preceded by its quotation. Yields the sentence when preceded by its quotation. So a quotation is just quoting something. It turns anything into a noun. But hello in quotes is a different word than hello. Because hello in quotes is a reference. So that's what quoting is, and it's integral to this. And the reason why it works is because he basically just made a machine that could generate any pattern that could be generated using a tape. And the tape had a pattern for the original thing, including the pattern for the tape. And so this will make a copy of itself and a copy of the copy, and it'll keep making infinite copies of itself.
Wow, I kind of feel like once again, Gödel Escher Bach, rears its head. Like these concepts are everywhere.
Oh yeah, he talks extensively about quines.
That's right. And then they also have a strange loop representation.
Yeah, because a quine is also a type of computer program that could output its own code.
Okay.
And you always have to have like a kind of like an internal machine that generates written code, and what I call a strange loop representation, which is basically you have to represent the code within the code, and it's very tricky. It's a good exercise for aspiring computer scientists, though. Cellular automata, as we've shown, have the potential for very simple behavior, but also very complex behavior that emerges from very simple rules. This is why cellular automata have been conjectured by some to be integral to the structure of the universe. Whether this is true or not, the field, like many we cover here on Breaking Math, is very new and very fertile, and there's a lot of research going on even at the amateur level. I'm Jonathan.
And I'm Gabriel.
And this has been Breaking Math. Today we had on
Chris Burnett.
And Chris, you want to plug your show again?
Yeah, my show's 10 Drink Minimum. We're on any kind of podcast catcher, iTunes, Facebook, all the cool social media sites.
I gotta say something. What I've found just really, really fun is when you actually go on, in this case, probably YouTube or Facebook, and you watch your live stream. You can interact with Chris and ask him questions live. Right. It's exciting. There's something exciting about seeing someone on TV responding to your questions.
Right. And we try to make it very audience based.
Yeah. So
nice. And how often do you come out with new shows?
We try to do at least 4 shows a month, and we do at least usually about once a month. We're out and about somewhere, whether it's a brewery or a festival or something. So
nice. So watch out for 10 Drink Minimum and listen to them. They're great. And if you are interested in Conway's Game of Life, then just go to conwaylife.com and you'll find a wiki, a whole community dedicated to the game of life.
Yeah. Cool, man. Awesome.
I know I'm dedicated to the game of life.
That sounds like a cult. Are you dedicated?
Save big this summer with great deals, all in the Baker's app. Get red, green, or black juicy seedless grapes for $1.88 per pound with a digital coupon. Then buy 2, get 2 free delicious 12 packs of Coca-Cola, Pepsi, or 7-Up, all with your card. Shop these deals at your local Baker's, less than 10 miles away. Or tap the screen now to download the Baker's app to save big today. Baker's, fresh for everyone. Prices and product availability subject to change. Restrictions apply. See site for details.
You dedicated?